Saxon Algebra 2, Lesson 115. Greetings, students. Let's talk about exponential equations, exponential functions, which are problems with exponents in them. Now, if I'm talking about exponents, from here on out, I can also be talking about logarithms because they go hand in hand and they can go by the same name. So let's look how the two link together. First, I'm going to show you how to do a calculation, and then we're going to learn a new style of word problems that will use this new technique to solve them. What if we have an expression like this? It's an equation that we want to solve. Okay, so we've got on the left side 10 with an exponent, and on the right side we've got 17. How can we solve that? What we want to do is turn this 17 into 10 with an exponent on it. Because then, and this is news, I didn't have any idea when I saw this come, I learned this, I never saw it coming. If we can write 17 as a power of 10, which our calculator can help us do, then once the bases match, you can take the exponents off and create an equation just out of them. What? You can. A second, I have to get my paper calculator. Here it is. So how do we turn this 17 into a power of 10? With our calculators, we know the number we have. We want the exponent. Know the number, want the exponent, base of 10. This button is the answer to our problems right here. If you enter 17 to your calculator, and then hit that button, what it will do is it will give you the exponent you put on 10 to get 17. And it will tell you, I don't think you need to hit the equal sign, but what you will get is 1.23. This is what we call the number. This button drives the base, and the calculation gives you the exponent. Interesting, right? So now we can take this exponent and put it here, 1.23. You can test this number if you like. Enter 1.23 and then hit 10 to the x, which is this button, right? So enter 1.23, then hit this function key. It will take the last, it will take the last number it gave you and put that in as the exponent, and you should get 17 back again. We can also test it for reasonableness because we know that 10 to the first power equals 10. And 10 to the second power equals 100. This is 10 to the 1.2, so we know that it's between, the answer to this is between 10 and 100, and we know because 0.2 is fairly low, we know that it's closer to 10 than it is to 100. That's another way to check that number for reasonableness. Okay, so we have figured out 17 can be written as 10 to the 1.23, and that's equal to 10 to the x plus 2. And like I told you, and I understand if you still don't quite believe that it's true, we can take off the exponents and create an equation just out of them. That is algebraically permissible. And then what we'll do is we will, let's see, it's x plus 2. I somehow changed it into minus 2. I guess because I was busy thinking about doing this. this cancels, and we'll get negative 0.77 equals x. That is the answer. Now, it doesn't have a lot of meaning or context, but that is the correct answer. That's the value for x that will make this come true, okay? So we used our calculators to convert this number to a power of 10, which gave us matching bases. And once we get matching bases, we can pop off, I know that's not mathese, but we can pop off the exponents, right? And that's what we did here. We got the bases to match, and then we popped off the exponents and solved them separately. Okay, we're gonna use that calculation later, but for now, we can move on from that. Exponential functions are very common in the world of science and in the world of business. We've talked about them before. It's actually this very same lesson, 115 in Algebra 1, we covered last year, and we did this. What we're gonna do is take the basic equation that we used for an exponential function, and we're gonna refine it a bit. This should look vaguely familiar. Last year, we used most of these terms, but one is different. A stands for amount. A to the 0 stands for the original amount. Or the amount when the time is 0. No time has elapsed, right? T equals the time. AT equals the amount at T equals the amount at T time. I know that sounds weird, but we'll put it like if it's 3 years have passed, we'd put in a 3. Okay, so it's the amount of time that has passed. E is our old friend, the natural log. And that's one thing that's really interesting about E is that it does describe growth of things like bacteria and rabbit populations. And I haven't seen the modeling, but I'm sure COVID too. K equals a constant. When we first looked at this kind of a problem last year, instead of using e to the k, we used just y, and we called it the multiplier. This is a more refined way to describe the multiplier. We have another exponent in there. T we had on the y last time. So we're swapping out the old simple way of just saying y, and we're refining it with this more complicated calculation. So that's what's happening with our equation and our variables. We'll come back to this, but I want to talk just a little bit about how exponential functions behave. There are two different basic types of exponential functions. The first is called a growth function. And I'm going to show you two so that we can compare them a little bit. Okay? And the grids don't really matter that much. This is t for as time increases, and this is a of t, the amount that increases. So I'm just going to put some numbers in here. We don't really even need those because we're not talking specifically. Let's say that that amount is 200, and let's say that this is, I don't know, weeks that go by. this expression, I'm not graphing it exactly, but here we're saying that this curve represents 200 times e to the 0.4 t. So our growth multiplier is driven, it's got the same base, but notice that the exponent is 0.4. Here's another one. And notice that with this exponential curve, it's not quite so steep. It doesn't go up quite so fast. This one, we're using the same constant in front, the same e, of course, that's a constant too, but look what's happened to the constant in our exponent. The greater that exponent, the faster the curve goes up. Okay? The graph for this equation goes up faster than the graph of this equation because 0.4 is greater than 0.2. Okay? We do sketch, occasionally we sketch exponential functions, but our graphs are very, I want to say generic. They're very simple. We don't get into a lot of details. Now we're going to do what are called decay functions. Sounds like something the dentist would be interested in. In these, we're going to have the same number, but really that's just coincidence. Instead of going up, what happens is that the amount of material that we have, whatever it is that we're measuring, is actually decreasing. We're going to get into a story of one of these later, so I won't make up a scenario for you. But in these, our constant in our exponent is negative. And as you might guess, this graph goes down faster than this one, and we don't measure it by the number here, but the absolute value of this curve is greater, right? Because the absolute value is 0.4. That it goes down faster because the absolute value of this number is higher, okay? So here we had positive numbers. Here we have negative numbers here and here, but the negative 0.4 goes down faster than the negative 0.2 because of the absolute value of those numbers, all right? So what I want you to see is that it's the constant in the exponent that drives the shape of the curve. All right. So that's good to know. Like I said, we will come back. And this is a good thing to know. When the constant in the exponent is greater than 0, you will have a growth function. When the constant in the exponent is less than 0, you will have a decay function. That is helpful because now what we can do is we can just look at our formula once we filled in actual numbers, and we can look at the value of our k and automatically know, is our curve going to go up or down? Do we have a growth or a decay? We can tell just by looking at that number. Happy days, right? Okay, let's look at an actual problem. In the beginning, there were 400 bacteria in the dish. Don't worry about the numbers. We'll come back for those. Just listen to the story and let's see if we can get a feel for what's happening. There were 400 bacteria in the dish. The number of bacteria increased exponentially. 3 days later, there were 2,000 bacteria in the dish. How many bacteria would there be in 8 days? Okay, so we don't have to graph this, but we can see that clearly we're dealing with a growth function. It starts at 400 and it goes up to 2,000 in just a couple days. So it's going up, and that tells us that that constant in our exponent should be greater than 0. All right, let's copy our formula so we have that. The amount that you have after a certain time period is equal to the original amount times e raised to the power of some constant and the time. It can be measured in weeks, days, years, minutes, eons, whatever you want. John doesn't usually cause any problem with that. In the beginning, there were 400 bacteria. So the amount at time 0 equals 400. The number of bacteria increased exponentially. Okay, that means we can use this. 3 days later, so when time equals 3, the amount after 3 days was 2,000. And we're supposed to find the A of 8. How many would there be in 8 days? That's the question. These are two-step problems. Like so many other problems that we've come across, the first thing that we do is we solve for K, and then we answer the question. And usually we get 2 sets of data. One set of data will help us solve for K, and then the other set of data will be used to answer the question. And we can see right away, oh look, there's some information about the time of 3, but then we're supposed to find the amount at 8. So the information after 3 days will help us solve for K, and then we'll use that to solve for after 8. Okay, so let's write down the information that we're going to use for the first part. We'll need the original amount, and we'll need the amount after 3 days. This is 400. And we'll need to know that the t is equal to 3. Now we're going to plug into this equation. So what we get is, I'll write it down here, 2,000. The amount after 3 days is, oops, one more 0, is equal to the original amount, 400, times e to the k, and then t is equal to 3. So we put this up here too. There's our equation. We have to solve this. We have to solve it for k. Oof. All right, well first let's get rid of this plain number. That's easy enough. Right? And we get that 5 equals, that all cancels, e to the, and I'm just going to reverse the order on that because K3 feels weird to me. 3K feels much more normal. Although, so this seems like the K9 unit at the police, and this seems like a 5K race. But whatever, I'm just spitballing now. All right, so now we've reduced our equation to something much smaller and simpler, but it looks really tough to solve until we remember that equation we did way back at the very beginning of this lesson. If we can change this 5 into e, which remember e is a number that means about 2.7, we can write 2.7 whatever with an exponent on it that will be equal to 5. Then we'll have e equals e, and we can take off the exponents and solve. You see what I'm saying? Okay, so what we want to do is use our calculators to turn this into a power of e. We take 5 and we hit this button, the natural log button, right? That stands for natural log. Don't ask me why it doesn't go NL. I don't know. Can't explain that to you. We know the number, it's 5. We want the exponent that goes on e. We don't want to use the base of 10 because that's not in the base of 10. We want the bases to match. So this is the button we use. It's as simple as going 5, then this, And in most calculators, you have to do equal. No, I don't think you do. But when you do that, what you will find, let me just show you. We do 5, and then we do natural log. I don't think you have to hit equals, but if it doesn't pop up with this right away, then do it. 1.61. That means that E, which remember is about 2.71 in the very same way that pi is about 3.14. If we raise that base to the 1.61 power, that will be equal to 5. Happy days. Now we can pop off these exponents, right? And we can say that 1.61 equals 3k. And now we're ready to divide by 3. Excuse me. And we can do this long division. We don't have to rely on our calculators. 1.61 divided by 3. It's not going to come out even because this adds up to 8 and 3 does not go into 8. But we'll take a shot at it. It goes in here 5 times, right? It goes in here 3 times because that's 9. And we'll get what? 2, and we'll bring down a 0. It goes in there. Oh, it's going to be just under. It's going to be 6 and then something big because this is almost 7, right? If this was 21, it would go in 7 times. So I'm going to trust that it would round, and I'm going to use this as my rounded answer. So I'm going to say that k equals 0.537. I chose to put the 0 here. As long as my decimal point is obvious, I don't have to worry about that 0. It's a stylistic preference. All right, so now we have a value for k, and we're ready to go back. All of that was step 1. I know, the problems have gotten really long, haven't they? Good thing you're smart and you can follow it all. So we solved for k, it's 0.537. Now we need to use that to answer the question. And the question says find a of 8. Okay, so we need to use this again. I'm going to copy it over here. A to the t equals a to the 0 times e k t. So what do we know? A to the 8 is what we're trying to find. A to the 0, oh, we still know that. That's 400. E, we know, our calculator knows it's 2.71, blah, 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 blah. K, we have right here, 0.537. When we're dealing with long decimal numbers and exponents, it's always better to go a little more precise. Put a few more digits in there because it will really change the value of the answer. Okay, and our time we know is 8. So let's take all this, plug it into this, and solve for t. So a to the 8 equal, it's actually, we say it as a of 8, not a to the 8. That implies an exponent. A of 8. Yes, a of 8 equals a of 0, 400, times e raised to the power of, I'm going to use parentheses because we multiply these, 0.537 times 8. All I did was plug all this information into that. Beautiful. Now how do we solve this? Well, calculator's at the ready. What we're going to do is we're going to multiply these together in the calculator. So we're going to do 0.537 times 8 equals, if you need it. Then this number is the exponent, right, that goes on e. So then we're ready to use this. We know the exponent. We just calculated it by multiplying. We want the number that represents. So then we use the E of X button. Shouldn't need an equal sign, but if you need it, hit it there. And then our last step is to multiply by 400. Multiplying by 400 is easy, but once we start a calculation like this in the calculator, we're gonna let it go. We're gonna keep it in the calculator till we're done. So we multiply together these two pieces. We calculate the value of them as the exponent on E using this button. This is the tricky one. These if needed. Then we multiply that by 400. Again, we use the strategy of working our calculations on the calculator from right to left. It feels a little backwardsy, but it's quite often the right way to go. So when we do all of that, we will find that the amount of bacteria that we will have after 8 days is 29,362 bacteria. Now, that is what I calculated when I used it with our decimal point, our decimal places at 3. John gets exactly the same, is that right? Yes, because he uses the same number of decimal places here. So this comes out exactly the same. Now, here's something I have to say about this kind of problem. They're annoying because depending on how you round your decimals, you may get a slightly different answer. So, if you hate coming up with different answers than John, check the solutions guide and make sure you're rounding to the same number of decimal places as John is in this part of the calculation. If you are fine with a little bit of ambiguity and you don't mind if your answer's close, then don't worry about it. I don't care if your answer's close as long as you're doing all of this correctly. Okay? So that's part of the reality we have to live with these problems is they're a little vague. Ideally, what I would want to do is when we calculated this 537, remember we rounded, if you could have more decimal places here, that makes the number even more precise, but that's kind of a pain, and I want your numbers, in the best case scenario, I'd like your numbers to match to John's numbers so you get that satisfaction of ding, 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 it's exactly right. Okay, so live with a little ambiguity there. The next one is the decay problem I promised you. Look, why did I write that like an exponent? Ignore that. I'm rewriting our formula here. Make sure you memorize this. I was just looking at the final exam today and there is one of these problems on it, so make sure you have one. Have it down. 2 steps. First we're going to solve for K, then we're going to answer the question. In the beginning, there were 4.25 ounces of radioactive material. Okay, the original amount is 4.25. Radioactive material decays over time. This is we're crossing the line into sciencey bits, but this is the classic decay function story problem, is that the radioactive material slowly breaks down, right? Very slowly. That's the whole story of Chernobyl, right? The nuclear plant that blew up a handful of years back. The site had to be abandoned and is slowly, that radioactive material is slowly decaying, but it's gonna take hundreds of years before that land is safe again because the radioactive material decays slowly at first and then it picks up speed. Okay, here's our radioactive material. John tells us it decayed exponentially. Good, that means we get to use this formula. 10 years later, so the amount after 10 years, 3.92 ounces remained. How much would remain after 30 years? Okay, I wrote this under number 1. No, that's not right, but whatever. This is actually part 2. So let's set this up. First we solve for k. So 3.92 fits with this, right? We're using a t of 3 for the first part. .92 equals the original amount, 4.25, times e to the k, we don't know, and we're using 3. How do we know that? Oh wait, not 3. This is 10. I had 3 here and I had 10 here. Something was wrong. So I went back to the book and realized I just made up the 3 that was in the last problem. It's actually 10 that is correct. So we're going to multiply our exponent also by 10. Again, next time around, I'll reverse that. I like the letter after the number. Okay, how do we solve for k? Same thing we did last time. Divide both sides by 4.25. .92 divided by 4.25. Let's go ahead and use the calculator to solve this. We get 0.9223 equals e to the 10k. Now it definitely is a race, right? So I use the calculator here. To do that division, okay? Now we need to take 0.9223, and we need to change that into a power of e, and then that will be equal to e to the 10k. So again, I know the number, I want the exponent. I know the number, I want the exponent. This is the button I use. So I will enter 0.9223 and then hit this button. And I will get the result that the exponent is that. This makes me nervous. A minus sign? Seriously? Well, spoilers, decay functions always have a k value that is less than 1. Remember I told you that back on the other page? If k is less than 1, then we have a decay function. So this makes sense. How do I know that this is right? Well, if this number was 1, then this number would be 2.7. So the fact that it's less than 1 actually makes me kind of happy because I want this number to be less than 2.7. So I use a few different, I think about this for a minute and say to myself, is that reasonable? The other thing I can do is check that number by using this button. If I enter if I enter 0.08, make it negative, and then use this button, I should get that number back, the 0.9223. So I can check and make sure it's right. Now I'm ready to pop these off, and I get minus 0.08 equals 10k. I divide by 10. Dividing by 10 forces the decimal to make this number one jump smaller. So I know that k equals minus 0.008. Now I have 2 zeros right here. I could put the 0 here, it's just stylistic. Oh my gosh. All right. So there's my negative value for k. It's less than 1. That tells me I've got a decay function. Okay, that's good. Now I'm ready to set it up to find a of 30. And I will say that the a of 30 equals the original amount, which was 4.25, times e to the k to the t, which is 30. Right? We're finding a to the 30. Our k is that. Our original amount is 4.25. I'm just plugging everything in here. Here, I'll write it again. Beautiful. And now we're going to evaluate this. That's what we call it. That's fancy math talk for saying shove it in the calculator and calculate. Again, we're going to start here. We're going to multiply 30 times this. Then we're going to use this button because at that point, we'll know the exponent. We want the number. Know the exponent, want the number. That's this button. So we'll use this button to evaluate this, and then we'll multiply it by 4.25. Again, we'll keep it all in the calculator. All right, and what we'll get is that the amount of radioactive material that we will have on hand after 30 years will be 3.34, and the unit we're putting on this is ounces. Is that the right answer? Yes, it is. Now, this is a great example. Remember how we were looking at those different rates of decay and saying that the larger the absolute value, the faster it goes? This is going really slow because we have such a little number. After the original amount was this, then we went down after 10 years, we went to that. After 20 more years, we're only down to that. It's not going away very fast. This is exactly the problem of Chernobyl. It's got radioactive material and it's not going away very fast. Sad story. Okay, so here we did a science growth problem with the bacteria in the dish. We did a scientific decay problem with the radioactive material. Now we want to do one more problem, and this one is going to be a business and a finance application of it. I know way more about finance than I do about science because I was an accounting major and I worked in the field of public accounting for 6 years when I was in my 20s. So I feel very comfortable with this topic and I'm going to try really hard not to tell you 100 stories, but I could. Okay, compound interest. Compound interest also behaves according to an exponential function. So that's really fun. And in order to do this, we're going to tweak the formula ever so slightly. We've been using this, right? For finance, business, whatever you want to think of it as, we tweak it so it looks like this. P stands for principal, which is the amount of money. We're talking about savings accounts, okay, or any sort of saving vehicle. The amount of money that you put in to get it started is what we're talking about. And R is the rate of interest. As you know, if you will invest money, really not so much in bank accounts anymore. A lot of bank accounts don't pay interest, but you invest in, say, a money market or a stock fund or a mutual fund or blah, 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 a bunch of different other financial tools, you'll get paid a rate of interest. So you put your money in, you leave it for a certain amount of time, whoever owns the assets will pay you interest, and then in the end, you will have an amount that combines your original investment plus all the interest that you earned. So these numbers are very similar, but we use different words to describe them in this application. Roger deposited $5,000. Okay, the amount you deposit is the principal. So what we just learned is that the principal he invested is $5,000. In an interest-bearing account that paid 7.5% interest. Okay, so the rate of interest is 7.5%. That's awkward. We'll deal with that later. Compounded continuously. That's normal. That doesn't change anything. How much money did he have in 10 years? Now, here's the nice thing about these finance problems. We don't have to calculate the constant because the rate of interest is information that's always given to you when you make an investment, right? Some investments are a roll of the dice and you can only calculate your earnings afterwards, like a stock fund. But some investments will promise you a certain interest rate, and that's the number we use there. So we don't have to do the calculation like we did there. That's happy days, right? All right, so to find the amount after 10 years, it will equal the original amount, the principal, times E to the rate of interest. Okay, this is 7.5%. How do we write that as a decimal number? 0.075. We can rewrite this as 7.5%, and then we bump the decimal place twice. So this is what our interest rate looks like. And then we're going to multiply that by the number of years, 10. Okay, so these problems are way easier because we don't have to calculate a K. We just use R, our rate of interest. All we had to do was adjust this weird fractional percentage to a decimal number, shades of middle school, and now we're ready to calculate. So grab your calculator and we work backwards. Again, this is going to involve this key. We'll multiply 10 times 0.075. That's the exponent that we want on E. So we'll use this one. We know the exponent. We want the number. We get that button, and then we multiply by 5,000. And what we will find is the amount of money that our friend Roger has in his savings account. He puts in the $5,000 and he just leaves it for 10 years. And look what happens. He's doubled his money and then some. Let this be a lesson to you, students. If you can save up some money at this stage of life that you're in, or shortly, in the next 5 years, say, throw it in an account that earns a decent rate of interest and leave it alone for 10 years, you'll have a lot of money. This is the right answer. So, saving money is super fun when you leave it alone and let it build. It is very cool. Okay, yay! That is the end of lesson 115. That is a long one, and I promise you lesson 116 is going to be shorter and cuter. Thank you, goodbye.